Final type of change that can be predicted using the Chatelier's principle is changing pressure. So really, it's pressure or volume, because in this world, we're going to be affecting gases. So we're going to be affecting gas molecules, and we know based off of Boyle's law that basically decreasing the volume is the same thing as increasing the pressure, or vice versa. So we're going to talk about these things interchangeably. A lot of times I like to use volume because that's like functionally what you actually do. You change your container size. But there's also a lot of pressure discussions or people will use that. And so when we have an equilibrium that's based around gases, so we do need to have gas molecules in an equilibrium for this to matter, we can think about that those gas molecules like to take up space. And if you increase the volume or decrease the pressure, right, low pressure, there is more space. This box is bigger. And so the equilibrium will shift to fill that space. The equilibrium will shift to fill that space. And so what will happen is if you go to a bigger box, you would get the equilibrium will shift to produce more gas molecules. You can see that's why this case there's more of the blue molecules, which are my reactants, because there are 4 gas molecules on the reactant side. I'm just counting reaction coefficients, so the 1 N2 and the 3 H2s. Conversely, if I were to increase the pressure, meaning I have a smaller box, you can see here that there's less space for all the molecules per molecule. So the equilibrium shifts to basically decrease the total number of gas molecules, and it shifts to the side with fewer total gas molecules. The 2 in front of the NH3, there's only 2 total gas molecules. So you can see this equilibrium we can control by changing the pressure or the volume, right, inversely, to basically, if we want the side, we either want more crowding to force the side with fewer gas molecules, or less crowding leads to the side with more gas molecules. And this is just counting the number of molecules in the reaction coefficients. So how will the reaction shift due to decreasing the volume of the equilibrium mixture? When I'm looking at this case, these idea of Le Chatelier's principle, I just want to key in on the fact that I'm changing the volume. So if I'm changing the volume, what that means is if I want to predict the direction of the shift, I need to be looking at the gas molecules. And so how is my volume changing? The volume is decreasing. So I am decreasing the volume of my mixture, which means that I am going to want fewer gas molecules. So which side has less gas molecules or fewer gas molecules on it? And so if I look at this first example, calcium carbonate solid reacting with calcium oxide solid to give me CO2 gas. I can see on the reactant side, I have no gas. There's no gas on the reactant side. And in the product side, I have 1 gas molecule. So if I'm decreasing the volume, I want less space per gas, this reaction is going to shift to the reactant side because there's this nice 0 over here. There are fewer gas molecules, right? So basically I can think about it. I'm literally crowding molecules. They're crowding the gas molecules. The reaction is going to shift, equilibrium is going to shift to relieve that crowding. So it's going to go to the reactant side where there's no gas, right? You're just basically consuming gas, relieving that kind of crowding. My second reaction is CO2 gas plus H2 gas gives me CO and H2O, both gases as well. In this case, again, I want to count them up. I can see all my coefficients are 1. So I have 2 gas molecules on the reactant side, 2 gas molecules on the product side. And we said we wanted the side with less gas. In this case, 2 and 2 are the same. There is no side with fewer gas molecules. So there's no shift. It doesn't matter how you change the volume or the pressure of this reaction, you will never get a shift in the equilibrium. You could get it temperature or adding in reactants and products, but changing the volume or pressure will not affect it. Similarly, if you just have no gas molecules, solids, like an aqueous reaction, the pressure on top of that liquid isn't going to do anything. It's only when you have gases and you have to have a different number of gas molecules between the 2 sides of your reaction equation. So why does this happen? And again, changing the volume is not going to change the equilibrium constant. Equilibrium constant, once you have your reaction and temperature, that's locked in. So say I have this reaction, N2O4 gas becomes 2NO2 gas. I have K, I have my equilibrium constant expression, and whatever the value for Kp is is going to be the value for Kp. I increase my box, I decrease my box, does not matter. So how does this cause a change? Well, if we decrease the volume, say I do a 1/2 my volume, my pressure is going to double. Okay, so my pressure is going to double. This comes from Boyle's law, that sort of inverse between pressure and volume of gas. So all my pressures have doubled, which means when I change the box size, I affect the values of the pressure that was at the previous equilibrium. Now the system is not going to necessarily be at equilibrium, so I need to start calculating my QP, right? Because I've changed it. Those pressures have changed. And so what ends up happening is I can do the arithmetic here, or the algebra, and kind of work through, distribute, all that kind of fun stuff. And I end up seeing that for this reaction, when I half the volume and double all the pressures, I end up with a QP that is greater than Kp. It's double here. So this system is going to shift towards reactance to reestablish equilibrium, which is consistent with the idea that decreasing the volume leads to the side with fewer gas molecules, right? 1 is smaller than the 2 over here. So we're going to go to the side with fewer gas molecules, which is basically what this whole thing is predicting. And so we can see it's this kind of balance between the change, the constant, it's always a 2, the factor in this case was 2 on all of the pressures, but there's some sort of balance between them with how that affects the actual 2 that comes over here. And so one of the things, this is why you don't get a shift when you have the same number of gas molecules on each side, because all those 2's just cancel out. You need those coefficients to all be different. Okay, one video left. Looking for any questions on participation 217. See you in the final video. Bye-bye.